Hello, everyone. I will get started in about 1 minute. Okay. All right, welcome back. Hope you guys had a nice vacation. In the Zoom room, I will be asking everyone about what they did, so be prepared to share something. All right, so what we're going to be talking about now is electric circuits. So this is kind of the AP Physics C, E, and M is divided into 3 parts. One part is electric fields, the other part is magnetic fields, and the third part is circuits. So that is, so we're on to the third part, and we'll be going through that. Magnetism was pretty short. Circuits is quite a bit longer than magnetism, but in order to complete everything, we have to understand magnetism first. Okay, so now we are talking about electric circuits. All right, and so the first thing I want to talk about are the key variables. In electric circuits. And so there are 2 key variables. The first one is electric potential difference. Now, in the context of circuits, I will be calling this voltage pretty much 100% of the time. Okay, but we learned about electric potential just without referencing circuits, so you don't need to discuss it in the context of circuits, but it is when we're talking about it in the context of circuits, it is voltage. So that is delta V, because it's a difference. All right, it's a difference, and so for that reason it is delta V. But even though it's delta V, in the context of circuits, we usually just write it as V. All right, so even though it means a difference between 2 potentials, we just write it as V. The second key variable is electric current, which I will just, when we're talking about, circuits, I will just call it flat out current, and I won't say electric. because there are lots of different types of current. You could have water current, you could have wind, you can have all kinds of different currents. So, but when we're in the context of circuits, I'll just say current. And so you're already familiar with that from magnetism, because currents are the source of magnetism. And that is the rate of flow of charge. And it is denoted by I. So if we wanted to think sort of intuitively about these quantities, voltage is basically a force causing current to flow. Okay, so it's a cause, and then current is the effect. So nothing will happen in a circuit unless there is some voltage somewhere. Okay, so you need to have a voltage, and then a current will begin to flow. So now let's start talking about drawing circuits. So the basic thing we could draw would be a wire. This is a wire. It's just drawn as a line. By the way, I think I forgot to say this at the top of the lesson, but this lesson is going to be review of circuits, and then starting with the next lesson, we will get into stuff about circuits that you don't already know if you took my class last year. So this is going to be kind of a review. Wires can have branches. So for example, you could have a wire that, I don't know, branches into 3 parts. So this is a wire that splits 3 ways. You can have wires that bend. That's a wire with a right angle bend in it. That's completely okay. So yeah, these are kind of different variations on wires. Another thing you can have is a battery. So a battery is basically, it is a source of voltage. Okay, that's why you need to put a battery in order to make your game controller work, or your remote control, or whatever on the for the TV, stuff like that. And so the circuit symbol for a battery is long line, short line, long line, short line. And then typically you would write the voltage of the battery next to it, so maybe 6 volts. Okay. And the positive terminal of the battery is the one with the side with the longer line. So what I mean by the positive terminal is that this side is the side with the higher electric potential. And this is the potential difference that the battery creates. So for example, if this side of the battery was at an 8-volt electric potential, then this side is going to be at a 14-volt electric potential. Okay? But like I said, in circuits, we almost exclusively talk about potential differences, not absolute values of the potential. Why is this the circuit symbol for batteries? Because the very first batteries that were created were made out of stacks of different materials. They were layered, all right? So you can actually make batteries by stacking together coins. I've done it before. It's a really bad battery, but you can take pennies and nickels and you can stack them, and in between each penny and nickel you put like a paper towel that's been soaked in salt water, And if you do that, you stack all those together, it's a basic battery. Okay, so batteries, the original batteries were made out of stacks, alternating stacks of different materials. And so that is the reason why that is a symbol for a battery. A battery will push current out of the positive terminal. Okay, it'll push current out of the positive terminal. So if this is a battery, here's the positive terminal, the current is going to be flowing out of the battery in that direction. Okay. Another thing I wanted to talk about is that batteries aren't always what provides the voltage. You could have different things providing the voltage, like a solar panel or a power outlet or things of that nature. And so in general, things that provide voltages are called voltage sources. So this is the symbol specific to a battery, but you can have other voltage sources. And the symbol for that is just a circle with a positive on one side and a negative on the other side. So again, this would push current out the positive terminal. And you would write how much voltage it provides next to it. All right. Another common thing that we will see in circuits is a resistor. And so what a resistor does is it controls current flow. So that is one thing that it can do. Another thing that it can do is it could actually be representing other objects. Okay, so for example, a light bulb is a resistor. Light bulbs, if you put a light bulb in an electric circuit, it resists the flow of current, okay? But in doing that, it provides us with light, okay? So we might draw the light bulb as just a resistor, but really it's representing something else. Another example would be an electric motor, okay? An electric motor is taking the energy from the battery, and it is turning that into mechanical energy. You're using the motor to accelerate a car or to lift a crate or something like that. But from the perspective of the circuit, that motor just looks like a resistor. Okay. So the symbol for a resistor. But then, of course, other times you are actually trying to control the flow of current, and so there are little things called resistors that you can put in. So this is the symbol for a resistor. It's just like a little jagged line. And typically you would put the value of the resistance next to it. So R is called the resistance. So resistors have a resistance, which is a parameter that describes how it behaves. Resistance is measured in ohms because the guy who studied resistors first was named Georg Ohm, and ohms are abbreviated by the Greek letter omega. So when you put current through a resistor, resistors are the opposite of batteries. So if you feed current into a resistor, The higher potential side of the resistor is the side that the current goes into. Okay, so notice how that is opposite from a battery. Okay, batteries, the current flows out of the positive side, and for a resistor, the current flows in to the positive side. Now, why is that? Well, it's because batteries are outputting energy into the circuit. Resistors are using that energy. They're taking in energy and either generating heat or light or lifting something or whatever they're doing. Okay, so it's the difference between outputting and consuming power. All right. So it turns out that there's a nice law called Ohm's law. And what it says is V equals IR, where V is representing the voltage across the resistor. I is the current through the resistor, and R is the resistance of the resistor. Okay. And so we could, of course, rearrange this. And so we have I equals V over R. And so this form of Ohm's law tells us why R is called resistance, right? Because the more resistance you have, the less current is going to flow. That makes sense. The more resistance, the more it fights current flowing through it, so it gets less current. You can see this equation also expresses the causal relationship between voltage and current. So the more voltage you have, the more current is going to flow. Okay. So let's just do a basic problem here. So this is the basic circuit. Suppose we have a 12-volt battery. And I won't always put the positive on the battery, but it's the longer line is the positive side of the battery. Okay. And then there's a 3 ohm resistor. And because this is the positive side of the battery, the current is going to flow out. It's going to bend at that corner. It's going to bend again. It's going to go through the resistor. It's going to bend again, and then it's going to go back into the negative terminal of the battery. Now, because this is a resistor and the current is going down through the resistor, this would be the positive side of the resistor. Okay? So we could figure out how much current is going to flow using Ohm's law. V equals IR. So because this battery is connected to a 12-volt battery, that means that the voltage it is going to get is 12 volts. And then the resistance is 3 ohms. Dividing both sides by 3, I get 4 amps is the current that flows. Okay. There's another useful equation, which is for the power output of the battery. And that equation is so this is the power. So remember, power is joules per second, energy per time. So it's the rate at which energy is leaving the battery. And it's equal, to the current output by the battery times the voltage that the battery provides. So in this case, it is going to be the current is 4 amps. the battery is outputting 12 volts. So the battery is outputting 48 watts of power, which is another way of saying it's outputting 48 joules of energy per second. And then the resistor is consuming 48 joules of energy per second and doing something with that energy. So it's either heating up its environment, it's lifting something, it's accelerating something, it's making light, it's doing something with that energy that's useful for humans. Okay, so let's talk about some common circuit connections. I'll abbreviate circuits as CKT sometimes. Common circuit connections. One common type of connection is called a series connection. And a series connection looks like this. Okay, R1 and R2. So you know that you have a series connection. So let me tell you how you know that two things are connected in series. All right. If you can go between the things without the wire branching. Okay, so it's very clear here that the wire is not branching. See, I can just go directly from resistor 1 to resistor 2. Okay. You can have the wire bends. Like you could have something like this. Those are still in series because I could just go from here to here. There are still no branches. The wire isn't branching off. And when I say branching, I mean something like this, where the wire is splitting into multiple pieces. Okay. You could have different things in series with each other. So you could have a resistor in series with a battery. That's a series. Okay. Let me give you some examples of things that are not in series. Okay. Oh, you could also have stuff in between. You could have something like that. And resistor 1 and resistor 2 are still in series because even though there's a battery in between them, there's still no fork in the wire. Okay? But let me show you something that is not series. If you had something where it's resistor 1, resistor 2, like that, and then the wire branches, see that? See how we can't go from resistor 1 to resistor 2 without this branch occurring. So this is not series anymore. All right. You could even have something like this. Maybe there's resistor 4. All right. So resistor 1 and 4, if you go this way, you might say that they are not in series, but they actually are, okay? Because, yeah, if you go from resistor 1 to resistor 4 this way, there are two branches in the wire, okay? But if you go the other way and you go around in this sense, you go from resistor 1 to resistor 4, and the wire doesn't have any branches along this path. So as long as there is at least one path where the wire has no branches to go from resistor A to resistor B, then they are considered to be in series. Okay. It turns out that from the perspective of the battery doesn't have the ability to know what is in the circuit. Okay. The battery doesn't understand the details of how you built your circuit. All your battery does is feel the resistance of the circuit. Okay, so it turns out that from the perspective of the battery, two resistors in series, the battery just sees it like a single lumped together resistor. Okay, and the value of that resistor is called R sub S. R sub S is equal to R1 plus R2. All right. And this equation generalizes. If you had three resistors in series, it would be R1 plus R2 plus R3, etc. So it completely generalizes. A really important thing about series resistors is that, or series things in general, series things have the same current. This is an incredibly important fact. Okay? So for example, resistor 1 and resistor 2, they are not in series. So in general, they will not have the same current. Why? Because the current that goes here is going to split two ways. Okay? So this current will not be the same as that current. However, because 1 and 4 are in series, they will get the same current. So that's because these two currents will then come back together and rejoin to make the original current. Okay? So this is incredibly useful and important. All right. The other type of connection you can have is called a parallel connection. And I want to point out that these are two common categories of the way things are connected. Okay? You can have things connected that aren't in series and they also aren't in parallel. Okay, that's completely possible. So what a parallel connection looks like is the wire splits. All right, the wire splits. You have a resistor or two different things in each branch, and then it immediately comes back together. Okay. And one of the ways you can tell, this is my favorite way to tell if two resistors are in parallel, is you think about the wires almost like a trail system, like the Claremont Wilderness Park. You know, you do the Claremont Wilderness Park, it has a whole system of trails back there that you can take. You can take different routes. You can go Johnson's Pasture. You can go Potato Mountain. You can go, you can go, what is it? Marshall Canyon. And then once you go those ways, there's different routes you can take. So there's all these different paths. And one of the things you can do is you can do loops. Okay, so you could do a lap in the Claremont Wilderness Park and come back to where you started. All right? And so we can think about circuits in the same way. All right? We can think about a circuit as a system of trails. All right? And if you can do a loop in a circuit where you only encounter two things, then those two things are in parallel. Okay? So you can do a loop with only those things. All right. So what would the loop be? Well, I can imagine going around this loop like so. And so it doesn't matter that there's a branch here and a branch here. It's just the only things that I'm encountering on those loops are those two resistors. Okay. So let me give you another look at two resistors that are in parallel. So it has nothing to do with the orientation of the two resistors. Like, this one's up and down, this one's side to side, but they're still in parallel because I could go around this loop and I only have those two things. You can have things that aren't the same in parallel. So you can have a battery in parallel with a resistor, for example, like that. Okay, so if I go around this loop, I only have the battery and the resistor, so they're in parallel. Let me draw a really weird parallel. What if you had something like this? These two are in parallel. Why? Because if I go around this loop, okay, I only encounter those two resistors. So they're also in parallel. But the interesting thing about this one is that these two resistors are also in series, right? Because I could go from here to here and there's no branches in the wire along that path. So this is an example of two resistors that are both in series and in parallel. That doesn't happen very often, okay? Let me draw something that that is not parallel. One and two are not in parallel. Why? Because if I wanted to do a loop around this circuit, do you see how that loop, it has 1 and 2, but in order to complete the loop, I also have to go through resistor 3. So that is not parallel. Okay, 1 and 3 are in series, because if I go along this path, then there's no forks. Okay. Just like with series resistors, it turns out that this is equivalent from the perspective of the battery to a single resistor, which I will call R sub P. And the value of R sub P, it's the same formula, it's just we replace the R's with 1 over R. So you have 1 over R sub P is 1 over R1 plus 1 over R2. And this pattern continues. So you could have 3 resistors in parallel. 3 resistors in parallel would look like the wire splitting into 3 parts, where any 2 of the resistors are in parallel. Okay. So that would be 1 over R1 plus 1 over R2 plus 1 over R3 is 1 over RP. Okay. Incredibly important thing about parallel connections. Parallel things have the same voltage. That's incredibly important, okay? So for example, these 2 resistors are in parallel with each other, okay? So that means that if we were to do Ohm's law on this resistor and Ohm's law on this resistor, we would use the same V value for each, okay? If they're in series, we're going to use the same I value for each. So this is really, really important and useful, as are both of these facts. Okay, and so I came up with a mnemonic to help you remember it. It's a really bad mnemonic. It's called SIPOV. Series things have the same current, which is represented by I. Parallel things have the same voltage. So you always want to remember SIPOV when you're analyzing circuits. All right, this is going to be a 2-pager, folks. All right, so CHL 412, period 7, part D. Next thing I wanted to talk about is combining batteries. Batteries can be combined. Oops. Combining batteries. Important thing. Parallel batteries. So you can put batteries in parallel. If you do that, they must have the same voltage. Parallel batteries must have the same voltage. Okay? And they must have the same orientation. All right? So for example, if you have 2 batteries in parallel, this is 2 batteries in parallel. All right, maybe this is 3 volts, maybe this is 3 volts. So these two have to be the same numbers, okay? And see how their positive terminals are connected by a wire. So that's what I mean by the same orientation. So this is equivalent to a single 3-volt battery. So you could ask the question, well, why would you ever put batteries in parallel then? If 2 in parallel is just the same as a single one, well, the reason is that if you have 2 in parallel, you can provide twice as much current, because maybe this battery has a maximum current and that battery has a maximum current, and these 2 currents combine right here at the junction and then make a super current. All right. Or if you don't need twice the current, you could use 2 batteries in parallel to provide the same current as you had before, but the batteries would take twice as long to run out of charge. Okay, so that's why you might do that. So let me draw some things that you would definitely not want to do. So you would definitely not want to connect them with opposite orientations. Okay. This is kind of like the snake eating its tail. So this battery pushes current out this way. This battery pushes current out that way. And the current just kind of circulates around and nothing happens. Okay, actually something does happen. You have a high chance of fire if you connect batteries in this way, because here the batteries are fighting each other, and then they provide a lot of current. Okay. Here the batteries are actually helping each other out, and so their currents are combining, and so there's going to be a lot of electric current in this wire, which means the wire is going to get really hot, and it's going to potentially start a fire. So this can happen if you are jump starting a car and you connect the batteries in the wrong way. It's possible to accidentally connect them in this way, and then you can have danger of a fire. So you would not do this. The other thing you wouldn't do is you wouldn't have two batteries that are of different size in parallel, regardless of the orientation. So, if this was 3 volts and this was 10 volts, that's not going to work. Okay. And the reason is that violates the SIPEV rule. Okay. Parallel things must have the same voltage, but this is a battery with 3 volts and that's a battery with 10 volts. It doesn't make sense. So if you do that, unpredictable things are going to happen. Okay, in order to make, so SIPEV is the dominant rule in this case. So if you take two batteries that have different voltages and you put them in parallel, something unpredictable is going to happen to make the voltages match. All right, so one of the batteries is going to be operating in a really weird way, or both. So you don't do that. If you have series batteries, then they add up. Series batteries add up. So for example, if you had a 12-volt battery and a 3-volt battery, and their orientations are the same, they are basically going to be equivalent to a 15-volt battery. Okay. I don't know why you would do this, but you could. So normally you connect positive to negative if you have batteries in series, but if you didn't do that, so you could do something like this. It would be really stupid, but here I'm connecting negative terminal to negative terminal of the batteries. So maybe this is 12 volts and this is 3 volts. If you did that, because the 12 volt is the larger of the two batteries, then that means that it's going to win out, and the overall effective battery is going to be pointed in that direction for its positive terminal, and then it's going to have 9 volts. So I don't know why you would do that. The only reason I can think of why you would do that is if you really needed 9 volts and you had no other way to achieve it, because this is very inefficient. All right, so we're going to do an example that kind of puts all this together. Okay. So let me draw out the circuit. All right. So this is kind of an interesting circuit. So the 20 volts is the dominant battery, so the current is going to flow this way down out of the positive terminal of the 20-volt battery. It's going to hit this junction. Some of the current is going to go this way. Some of the current is going to go this way. All right. The current that goes this way is going to hit this junction, and some of that current is going to go this way. Some of that current is going to go this way. Okay. Those two currents are then going to meet right here and come together again to make the original current. So the size of this current is going to be the same as the size of this current. And then that current is going to meet up with this current that has gone around this way, and those two will combine to make a current going down like that. And this current is the same as that current. Okay, so you have this current that's coming out of the batteries, branching, and rejoining eventually before entering the battery again. My question is, what is the power output of the batteries? Okay, so what we want to do is we want to identify series or parallel combinations. So immediately I see that these two are in series because they can be connected by this wire. There's no fork in that wire. So R sub S is going to be 20 plus 20 equals 40 ohms. These two batteries, I combine them just like I just did, and they are equivalent to a 14-volt battery that has its positive terminal going downward. So now what I'm going to do is I'm going to redraw the circuit, making those substitutions. Oops. Okay. So notice how these two resistors have been replaced with their equivalent resistance. These two batteries have been replaced by their equivalent. Now I see that these two are in parallel. How do I know that? Because I can do a loop. I can do this loop right here. That loop only has those two resistors in it. So I do my formula. 1 over R sub P is 1 over 40 plus 1 over 8. In the interest of time, I already did this problem last period, and I know that R sub P is 6.7 ohms. So now I redraw the circuit again. Ohms, 5 ohms, and I'm replacing these two with a single 6.7 ohm resistor. 3 ohms. Okay, now I see that these two are in series because I can go from here to here without the wire forking. If I go around a different way, it does fork, but remember, it only, if there is a single path that doesn't fork, then they are in series. Okay. So R sub S is going to be the sum of those two, 9.7. Redraw the circuit. Oops, 9.7 ohms, 5 ohms. Okay, so this is probably the trickiest part. All right, these two are in parallel. How do I know that they're in parallel? Well, if I go around this outer loop, that outer loop only has those two resistors on it. So that must mean that they're in parallel. Okay, so that means that 1 over R sub P is 1 over 10 plus 1 over 9.7. So that means R sub P is about 4 ohms. Okay, so now I'm going to replace those two with a single resistor. Single 4 ohm resistor. This one was 5. So now I see that those are in series because I can go along this path and it has no forks. It has bends, but it doesn't have forks. So we have R sub S is 9 ohms. And so then I have reduced it down to a single battery. and a single resistor. That single resistor is 9 ohms. And this is a 14-volt battery. So once you've done that, once you've got a single battery, a single resistor, you use Ohm's law. V equals I times R. The voltage is 14. The resistance is 9. This says that the current is 1.6 amps. And then power is current times voltage. So that's going to be 1.6 times 14, which is 21.8 watts. And that is the power output of the battery. All right, I will see you in the Zoom room. Have a great, I'll see you in the Zoom.